here's another problem. Now this problem is going to be involved lots of things going on. So here, let's understand what's happening. There is a block of mass m. Let's call this block 1, and we have a second block here. So block of mass m slides down a frictionless hill. So there, no friction anywhere. It's frictionless hill. It slides down a hill of height h, and at the bottom it collides and sticks with another block of mass m as well. Okay, and then they move together, and then they go and compress the spring. Our final ultimate goal is to figure out the spring compression. So you want to know, what are all the things that we're going to use to figure the spring compression out. Okay, so the first thing is, again, you have to ask, can we break this into lots of situations, because there's lots of things happening. One is the block's going down first, then it's colliding, and then they're compressing the spring. So there are three things that are going on. Okay, so the first one we'll do is find the speed at the bottom of the hill. So V at the bottom, we need to know that speed at the bottom. Okay, for block 1 we need to know that speed, because once we know that speed, we can then figure out the speed after the collision. So we need to know the speed before the collision for block 1. Okay, so in order to do this, we're going to use MEI equals MEF. I hope you've realized that. Okay, everything is frictionless, life is good. So in the beginning, the block 1 only has potential energy. Its kinetic energy is 0. Block at the bottom of the hill, this is all for block 1. So at the bottom of the hill, block 1 has no potential energy, but it has all kinetic energy. So 1/2 mv square plus 0. Okay, so this gives us the speed v at the bottom, which if you calculate will end up being square root 2gh. Very good. Now let us look at the collision. The collision is a perfectly inelastic collision because they get stuck together, which means that Pi is equal to Pf. We can use that. Now let's write Pi. Pi in the beginning is simply block 1 multiplied by its speed, square root 2gh, plus block 2 times 0 because it's at rest. And in the end, since they stick together, we have m plus m moving together with some speed Vf. Please make sure that you label them separately. Okay, so Vf is going to be equal to m times square root 2gh divided by 2m, which is equal to 1/2 times square root 2gh. Great, we have Vf. Now for the spring compression, okay, it's all moving on a frictionless surface. So we can now use, once again, MEI equals MEF and figure this out. And right after the collision, the mechanical energy is, since they're moving as one unit, it is equal to 1 over 2m, half times 2m times Vf square, which is equal to 1/2 times square root 2gh square, plus the spring is uncompressed, so that is 0, and the potential energies for the mass is 0. We don't have to worry about that so now, but let's just make a note of that anyway. So it is this 0 plus 0, and this is equal to the kinetic for the mass is 0, the potential for the mass is 0 at maximum compression, and all the energy is stored in the form of the spring's potential energy. Okay, so this is what you get. So the half cancels out, this half cancels out, this half and this two rather cancel out, and then all we are left with, there is an m here, and if you do this carefully, what we end up getting is m over k, or rather 2 times m over k times 1/2 times square root 2gh square is equal to x square. Okay, and from here we end up getting x is equal to square root 2m over k times half of square root 2gh. We can just leave it like this. Okay, in fact what we notice is that the 2's can cancel, the 2 square root 2's multiply, and we end up getting square root of mgh over k for the answer. Okay, so again, a problem that involves several things. There is a drop, then a collision, and then there's another further compression. So you can see many applications of problems of this sort where one thing, several things are going on. We'll look at a few more before we move on to our next topic, which is the elastic collision. Alright.